Hello. So we left our review today and we were talking about direct current and alternating current. And the advantages and disadvantages we didn't discuss. So, what are we doing with direct current versus what are we doing with alternating current? And direct current is able to go short distances, like through the circuits of your computer, or you know, not long distances. But we still have alternating current going through your house. So that seems like a short distance, but you still want alternating current even going those distances. So alternating current can do longer distances. Okay. Load demand. So DC is good for low load demand. And by load demand, we mean resistance. Think resistance. So that's what they're good for, and this is a thing that alternating current is good for, and it's good for charging batteries and whatnot. It's really not. Batteries and capacitors can be charged for DC to use locally. Sure. Right. How would we want to say that? I mean, you can't even charge batteries. I don't know. Basically, there's not a lot here. There's the longer distances that you can transport power. Once you get DC has everything. DC does everything great. All right, DC, but only in the short distances. Right. Every time you want to transfer power or electrical energy or whatever, you need to do long distances. Energy. It all comes from AC, is the way to go, and then you just convert to DC when you get there. So the only reason that it's okay is because of the cheapness, the inexpensive transformer. And allows it. So AC has one thing going for it, and that's pretty much it. Everything else, batteries, all those things, capacitors can be charged up with DC, and you really just need a rectifier to go. So rectifier. Why would I put a Y on the end of that? Rectifier to go from AC, boom, through a rectifier over to DC, where you can actually get stuff done. So, yeah, that's the nature of AC and DC. AC really is simply just to maintain our power. So, maintaining the power structure for the man. Okay. So, a short circuit supplies a lot of current, and this is part of the dangers of electricity. So, of course, there are a lot of dangers, and we talked about them in the one video. Everything was discussed, so I'm not going to do a whole bunch on this, but a short in your circuit short will start fires because of the heat that gets generated. So there's that. And then the second one is stay out of becoming part of the circuit. So don't mix it up. Don't become part of the circuit. Because it could hurt you. It could do a lot of damage. And we talked about all the different damages that it could do. So what do we do to minimize those things? We use fuses and circuit breakers. Okay, and we talked about how those things happen, how those things work, right? So do those things, and then, yeah, we talked about those. So I'm going to just keep on trucking through here. Our next topic is resistors in series and parallel. We've talked about resistance. So resistors in series and parallel. Series. Let's do series first. RS, which would be R equivalent for some resistors in series, you would say that that is equal to R1 plus R2 plus R3 plus however many you have in series. So what does that look like? That would be first R, second R, third R, and who knows how many you have going after that. So these are all in series. Now we could do parallel, and the arguments for series and parallel we've totally discussed. So we don't need to go through that again, but the parallel equivalent, which would be REQ, is 1 over R1 plus 1 over R2. And this can become quite complicated if you have a whole ton of them. It can get complicated, or if you got to do a combination of these two things, you break it down into little parts and you add them up. But dot 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 in that direction. Here's our R1, here's our R2, and here's our R3. And then who knows how many we would have. We could have unlimited amounts. So this is how you would add them together. Now, keep in mind, current flows through the path of least resistance. So if R2 has the least resistance, it's going to get the most current. Okay? And there's no way around that. All right? So path of least resistance, that always works. And you can see it best when you're looking in this parallel situation. Okay, what's next? The electromotive force. EMF is equal to, a lot of times you just see it written like that, but that's the electromotive, put a little E on there, force. All right, electromotive force. So, is this really a force? No, not a force. It happens to be something that is an electric potential. Okay, it's in volts, and it wants to push charges around, right? It's a potential for charges, and then they want to go in a certain direction because this potential has been set up. So, is it a force? No, but it really is a thing. So here's how it works. So let's say we have some battery. There's the positive side, there's the negative side of our battery, and I didn't do what I was supposed to do down here. We need to put a little internal resistance in our battery, because every battery has internal resistance. So this part is straight up EMF, okay? And so that means that we have a total voltage from, let's call this A, let's call this B. So we have a total VAB, and we have to do a thing where we say, okay, whatever the current is going across this resistor, then that is going to equal our EMF. Okay? All right, so a lot of the times we're given the EMF. We're given this. We might have to find this. That's okay. And then you're asked typically to find that. So what do? You go, okay, well, my terminal voltage, which is VAB, terminal voltage, boom, boom, boom. Let's do this a different way. I don't want to do that. Let's say VAB is equal to our EMF minus our current times our internal resistance. This is the terminal voltage. So, great. So when you say you have a V battery, it's not necessarily the EMF, okay? So we're not sure, unless you start talking about the internal resistance of the battery. If there's zero internal resistance, then of course your V battery is equal to your EMF. But if there is internal resistance, then these are not equal. All right, so there you have it. As long as this is not zero, you have a difference between your EMF and your battery. All right. All right, so what is our current in a situation where we have, let's do a situation where we have some EMF, we've got some internal resistance, and then we've got a resistive load. All right, so there's our EMF, there's our RINT, and here's our R load. So then we could say, oh, well, our EMF is equal to the current times R equivalent. And that means, what is the R equivalent? Well, these guys are in series, right? RINT and R load are in series. So we can say the equivalent, since they're in series, we can just add RINT to R load, and that's great. Now, we can then solve for our current, and our current then is our EMF over our internal resistance plus our R load. Okay. Next page, please. We are going to now look at Kirchhoff's rules. Good old Kirchhoff. You know what? I don't know how to pronounce it. I took German in college, and I wanted to learn, but it's Kirch. So this is the first part, and then Hoff. So Kirchhoff rules, I think is the German pronunciation for it, but okay. So what do we got? We've got our EMF, and we've got all kinds of crazy things happening in this circuit. We get to some point A, and then we've got this, we've got this. We're going to come down here, we're going to do this thing, and then we're going to come from there, and we're going to go this way, and then we're going to come down here and go like this, and then we're going to come over here, and we're going to come like this. And there's no internal resistance unless you want to call some of these other guys internal resistance. It doesn't matter. But no internal resistance. So let's label these things. R1, R7, R6. Down here we've got R4. Over here even further we've got a big mess. Right over here we've got R3, R5, R2, and R1. So where everybody's labeled. And then you label the current, right? But the current across R2 is I2. Well, it happens to be the same current because these guys are in series. So there's current going here, but it's I3 if you want to do it properly, but I3 is equal to I2, so I'm just going to call it I2, so we don't have a million different currents to keep track of. And we're still going to have current I4 going across I4. I5 is definitely different than any others. So I5 happens there. Why do I know that? Because this is a junction, right? And we're doing the junction rule. So we've got I2 coming in here, I5 coming in here. Every time I say I5, I think of the highway in Southern California. Anyway, I4 is leaving, okay? So we know that I2 plus I5 equals I4, right? So, okay, so there's our I4 going that direction. We've got I6, not a highway in Southern California, and I7. And then, of course, I1. All right, so let's do one of the rules. The junction rule is the first rule, and it's so much easier to handle than so one is called the junction rule. Where does the junction rule come from? It's based on the conservation of charge. So we would say conservation of charge. It just means that all the charges going in to a certain junction, let's do this junction, all the charges going in equal all the charges going out, right? Conservation of charge. So what do we have? Going in, we've got I1. So I1 better be huge, right? Here's a junction for you. And here's a junction for you. So this would be, I'm going to call this I7B. And we could call this I7A. And we know that I7B is going to be equal to I4 plus I6, right? And then that's going to add to I7A and give you the total I1. All right, so we could say I7A plus I7B is going to equal our I1. Okay, so that's 1, but then we've got up at the top, so all we did was this one down. Oh, nice work. All we did was this one down here. That gave us this junction rule. Now let's do this one up there, and we're gonna have. Don't worry, I'm not gonna solve this whole thing. I just want to say that I1 is equal to I2 and I5 and I6 and I7A. Okay, so this is an equation here. This is an equation here. And this is also, we can double up and say that's an equation because they both happen to equal I1. So for whatever that's worth, you can also figure out I7B because I7A drops off pretty easily, and you have I7B is equal to I2, I5, and I6. All right. Anyway, that's junction rules. Fine. Now, I hope you got the junction rule thing figured out because that's pretty easy, and I'm going to erase all this with my super fast eraser. We're going to erase that, and we're going to start talking about the loop rules. Okay, this is the harder bit. So this is the second rule. It's called the loop rule. And this one happens to be based on the conservation of energy. So the junction rule is energy. The junction rule is conservation of charge. This one's conservation of energy. Fine. So what do we do for the loop rule? So now all we have to do is start defining different loops. Fine. Let's do this loop 1 as our example. Well, should I do that loop as an example? You know what? I do that loop as an example in the notes. So let's pick a different loop to do as an example. Let's do this loop here. Okay, so let's call this loop 3. Okay, because this is 1, here's 2, here's 3, right? Here would be 4, and then on the outside we'd have 5. So here's loop 3. So let's do loop 3. All right, so loop 3, I've drawn how we're going to go around the circuit. Every time we're going with current, gives us a minus voltage drop. Okay, so if we're going to start, let's start up here at the top, and we're going to go this direction all the way around our loop. Okay, so we're starting at the top. So we're going with I5, R5. And we know that we're going to have 0 after our whole loop. We have 0. So we say I5, R5, but that's negative. And then I4, R4 is also negative because we're going with the current across R4. And then we're going upstream. Okay, so we're going upstream, so we're going to say I6, R6 is added, right? So we do a voltage drop here, voltage drop there, but this one is a voltage increase. Okay, we're going upstream. So fine, we've gone upstream, we've got our 0 equals those things, so we could then say I6, R6 equals I5, R5 plus I4, R4. So that would be one of our equations that we come away with. How many equations are we going to come away with? Well, we're going to have a lot. We're going to have our first loop, our second loop, our third loop, our fourth loop, and our fifth loop. So we'd have 5 equations just from the loop rule, and we'd have also many junction rules. Okay? So we'd have 4 equations from the junction rules, 5 equations. This circuit would give us 5 plus 4, that's 9 equations for that circuit. And we really only have 7, 8. We have 8 things that we could possibly figure out. Let's see. Is that right? No. We have 7 resistors, so there's 7 things. And then we have 8 currents. Oh, we have 15 things that we could be possibly trying to figure out. So we have 9 equations, but we have 15 things that could be known. And I'm saying 8 because we have I7A and I7B. So we have 15 7 resistors. And 8 currents. So those are the 15 things. So if we have 9 equations and 15 things, all I have to do is go through and give you 15 minus 9 is 6. So I would just have to provide 6 things, right? Oh, we need 16 because I didn't count the one EMF. We got to have the EMF. So 7 resistors, 8 currents, and 1 EMF. So what does that give? What does that make it? We got to change this to a 16. 16 minus 9 is 7. So we're going to have our 7 things have to be given. And if I give you 7 of those things, then you will get, you can get the other 9 things from the 9 equations. Might not be very fun. You probably would not have a good time doing that. Or maybe you would have a great time doing it. People play Sudoku. I love Sudoku. And it's a very, very similar thing. So, fine. Okay. I left the one on the first loop in the notes, so you can go through and look at that first note. I haven't ever done this for a class before, where I actually show you behind the scenes, but this is how I operate. When I'm doing problems, I want to make sure that people have what they need to get the answer. So I go straight to the equation and then go from there. Okay, so fine. Let's talk a little bit about DC voltmeters and ammeters. We're on page 44. DC voltmeters and ammeters. All right. A voltmeter, ammeter. I'm just going to, we all know that you can do these things with a galvanometer. Both, right? And then it just depends on how you set up your galvanometer to do either one, okay? That's nice. Nowadays, everybody's got a digital voltmeter. But it operates on the same principles. It just does it digitally with diodes and other assorted digital components. But galvanometers are nice because you really can't destroy a galvanometer, but you can destroy a digital voltmeter. Ask me about it sometime. I'll tell you what happened. Many times, actually. Digital voltmeters. I prefer a galvanometer because I just oh, what does this do? And then fry my digital voltmeter. Okay, so let's talk about a voltmeter. It would be nice if we had a T in there, voltmeter. You want to connect it to 2 points. It doesn't, this, not drawing it out is not super great. So I'm going to draw out what I'm talking about. So let's say we want to measure the voltage drop across this resistor. We've got some resistor. And we hook up at point A and point B, we hook up something that we can measure the voltage across those 2 different points. Okay, so we attach here and we attach there. And then we get a little current. Some little current gets shunted away from the normal current that would have gone through there. Okay, so we want to do as little as possible, right? So what does that mean? If we want a little bit of current to go through here, but not very much, that means that this voltmeter has to have a large resistance. And it has to be a lot larger voltmeter than our, we can call it R load, than R load. Okay, so our voltmeter resistance has to be a much larger than the load on whatever we're running current through. So fine, you can do that. You can configure something that'll do that, and you'll still alter the circuit, right? This is really important. No matter what happens, some of the current has to go over here through the voltmeter, and some of the current that would normally have gone through the actual circuit. So anytime you go to measure a circuit, you're going to alter the circuit, okay? So there's no doubt that that's going to happen. Now, when we do an ammeter, we're going to have that same resistor, okay? But we aren't going to grab at different points on this, in this situation. We're not going to grab different points because we want the current through, right? We want to measure the current through. So what do? We say, okay, let's insert our ammeter right here. And we start to measure the current as it goes through this thing. So again, we've got a galvanometer here, and we've got current that would normally have gone through our resistor. Let's call it the load. We've got our I current, our I load going through the R load, but we have inserted something that has resistance. Has resistance, right? Otherwise, it wouldn't be measuring anything. So it has to have resistance. So this is the resistance of the ammeter. Well, we don't want to alter that current very much at all. And that current is going to change based on the voltage from here to here. So VAB is equal to IR. Okay, but our R would be the R equivalent. And we want to get that R equivalent to be as close to RL as possible and yet still allow us to measure the voltage. So it's really changes, right? If we had I load, R load, that's fine. But our R equivalent is in series. So R equivalent happens to equal our resistance of the ammeter plus the resistance of the load. So no matter what happens, this is going to change, which means this is not the same as this, right? Close. We can make it close if we make this ammeter really, really small. So our ammeter has to be really, really small compared to the load. If that's the case, then we can make it really close. But we've still, again, altered our circuit. Okay, so anytime you try and observe something, you're altering the circuit. Okay, so altering. This is a thing, observational effect. Okay, so the observer effect, and it's a real deal. And mostly we notice it in quantum mechanics, right? You guys are like, no, not right. I don't know. What are you talking about, quantum mechanics? Quantum mechanics, this is a big deal. As soon as you observe something, then it's true, okay? Whatever you have observed was exactly what happened. And then all other possibilities go away, all right? Well, it's not quite as drastic as that. And as you go into classical things. It gets less and less dramatic, and what we're dealing with is classical E&M. So classical electromagnetism, we're still going to see it, but we're going to see it when it comes up in this type of way. So IA, let's solve for IA. No, let's solve for the difference between IA and IL. Can we do that? No. Let's just solve for IA. I mean, we could, but let's not. Let's do IA equals RL over REQ times IL. IA equals RL over RA plus RL. Okay, so our current that we get through the ammeter is almost the same current as we get through the load normally, but we are definitely dividing by this. Okay, now it would be a 1 if there was none of this, but it's not. There's a little bit there. Okay, so it's not going to be RL over RL. It's going to be RL over RA plus RL, and no matter what happens, you have RA. So that's us seeing the observer effect. Anytime we do something, anytime you look at something, your observer is altering the scene. I mean, just look at monkeys in a zoo. They know you're watching. Okay, so should we get back to RC circuits? Let's move on to RC circuits. RC circuits. RC circuits are great. And I have a little note about Kirchhoff's rules applying to RC circuits. That's true. They do apply to RC circuits. There's also RCL circuits, and L is an inductor. And we aren't talking about those either. So not only are we not talking about inductors in this class, we're not talking about how you can apply Kirchhoff's rules to RC circuits. So there's quite a bit, right, that we're not talking about, but everything that we've done still kind of applies in those same ways. So we're not, essentially, you can apply what we've taught you and do all the things that you need to do if you were going to increase or do larger types of circuitry work. Okay, but we're just going to stick with the basics: resistances, capacitors, and EMFs. Okay, that's it. All the rest, inductors and diodes, and I mean, it gets so complicated. There's whole classes. There's PhDs in electrical engineering. Okay, so it gets messy. If you want to, it can. So all we're doing is we're saying with an RC circuit, we are just saying that we are looking at circuits that have both resistances and capacitors, plus of course an EMF. All right, so what do we look like here? What do we have? We've got some EMF, so we've got a battery. Our battery's going to come off. Let's put a little switch in there. We can close that switch later, and then we'll have some resistance. Every time I say resistance, I want to say resistance is futile. And there, we have a capacitor. Okay, and we can close the switch at any time and magic will happen. So, first thing we do is close the switch. And that's going to complete our circuit. All of a sudden, flow is going to happen. All right? And initially, once we've closed that switch, we have our current is equal to the very initial current, okay? That's going to go through this whole system. Initially, the capacitor is not there, okay? So V equals IR, and that is it. So I naught is equal to our EMF divided by R. All right? That's just the way of the world, because the capacitor really doesn't do anything to stop or slow down that flow. However, soon as charges start to build up on this guy, it's going to slow down the current, because on one side we have positive charge, on the other side we have negative charge, and eventually that capacitor is going to get, eventually the capacitor will become a large enough voltage, so the voltage of the capacitor will eventually become epsilon. So this, our EMF. So this is what happens in the end. Okay, so at the end, our current, our final current, will be 0. Okay, because once this has the same voltage, except it's pointing in the other direction, once it has the same voltage, then we're done. This capacitor is fully charged, is what we call that. Okay, so what kind of equations do these operate on? So our V capacitor in the end ends up being this. What are the equations that do this? Inquiring minds want to know, and we're here to help. So we do this thing where we take R and C and we get our time constant tau. Okay, so that's the RC time constant. Okay, RC. All right, so tau equals the RC time constant. You take the resistance, you multiply it by the capacitance. Believe it or not, you get seconds as your SI unit, and it really is time. Okay, so it's not bull. This actually works. So what does that look like? That means that our VC, so our V across the capacitor. Now this is at any time, not at t equals infinity. This is at any time. So we can solve this little equation at any time. So whatever our battery EMF is, let's put a little battery there. Okay, so whatever that is, we're going to multiply that by 1 minus e to the minus t over tau. And of course, you have to substitute in RC for tau. However you want to do that, that's fine. But this equation is when we're charging a capacitor. All right. Now, when we're discharging a capacitor, we have a similar equation. We still have to operate on that same scale, but we are decreasing our voltage across the capacitor. So when it's decreasing, I don't know if you guys know this, but e to the minus t over tau looks something like this as a function of time. Kind of looks like this. Okay, gradually as time goes to infinity, it goes down. Okay, this graph is 1 minus that. So 1 minus that means it's going to go up to V cap in the end, which would be our E battery in the end. So we start out at our V max. Well, whatever our voltage max was, it could be E battery, it could be it could be all kinds of stuff, but we're going to multiply that E max, V max times R minus E over tau. And there you go. So at t equals 0, we're at this point. And this is our V max. I'm not going to say it's equal to the battery max because it could be or could not be. It all depends on the circuit. Okay, so I'm just going to call it V max and leave it alone there. So this one is charging, this one is discharging. Okay, discharging an RC circuit. Well, I shouldn't even say that. It's discharging the capacitor in an RC circuit. Okay, so we have pretty much done all that we can do with the electro side of the electromagnetism. So electro is complete, and we're left with magnetism, right? So electro and electromagnetism. All right. So in fact, we can erase that bit and we can just capitalize magnetism. All right, that's where we're at. Now, magnetism, we talked about initially when we started doing this review, what magnetism is all about. Well, first of all, we're dealing with a B field instead of the E field, F-I-E-L-D. And the B field only comes when we have a change in current over time. Okay, we're not if none of this stuff happens, if we don't have current, you're not going to get a B field. Does it have to be a change in current? I don't even think it has to be a change in current. I don't know why I said change in current. I don't think you have to have change in current. You just have to have current. Okay? So you need to have charges flowing. So let's say it like this instead. Current gives us an B field. All right, so we've got current. Well, the very basic thing that we could have is an atom. So let's draw our atom with a nucleus. And I like green for the electrons for some reason. So we're going to go around the nucleus with these electrons. They're doing their thing. And we can say there's an electron, and there's an electron. You get an electron, you get an electron. And these guys are going to go in a circle, which means that current is going in this direction. Okay, because the electrons go in the opposite direction of our current. So we've got current going in that direction. Now, what way is our B field going? I'm going to use blue for our B field. We put our thumb along the current, curl our fingers into the B field. So on the inside, it's going into the page. On the outside, it's going out of the page. And that's it. I mean, that's the essence of our magnetism. All right, and we've gone to the smallest possible development of magnetism, which is an atom. Should I say smallest possible? No. All right, well, for our sake, we're not talking about subatomic physics or any of that stuff, so we don't care about any of those other things. We just want to talk about the magnetism as a result of this super small situation. So that means that B fields have no monopole. No monopole. Because there's nothing else. It's just current. Okay? So the real thing is the electric field. The B field is a measured offshoot of the electric field. Okay? You can measure it, but indirectly, there's no monopoles, so it's just kind of an offshoot thing. All right. B field, B field, B field, B field. We get, I'm going to go straight to Lorentz force law. So we can say that the magnitude of the Lorentz force is QVB times the sine of theta. And I'm going to draw QVB. So let's draw B this way. And instead of doing it how I do in the book, I'm actually going to draw our particle going, our charged particle going in this direction. So there's V. And that means that we've got this angle theta between V and B. And we can then get our force. We do V, we put our fingers along V. All right, so it's a cross product, guys. I don't know how else to say this. The force is the cross product. So QV cross B. Cross product means that you put your fingers along the first vector, you curl them to the second vector, which is our B vector, going up the page, and you get your resultant by which way is your thumb pointing. So which way is your thumb pointing? Well, V cross B ends up giving you a thumb pointing straight at you, okay? So our force has to be out of the page. So we come over, we select green, and we go like this, and that is the direction of the force. So we have figured out the magnitude of the force because we have this force, Lorentz force law. We can figure out the magnitude. The direction is going to be out of the page in this situation. Okay? So the plane that describes V and B, there's V and there's B, this plane is the whiteboard. It's the screen that you're looking at. And it doesn't matter what this angle between them is. It could be a very small angle. Theta can be a very small angle. It doesn't matter. V cross B is still going to be out of the page. Okay? So that's something that a lot of people might misinterpret. They might say, oh, well, which way does F really go? It really is, these guys define a plane, and then this would be perpendicular to that plane, okay, that's defined. It could be 90 degrees, that is easy to see, but it could also be other angles as well. So we get our magnitude of the force here. We get our direction from the right-hand rule. Our V cross B gives us that right-hand rule direction. No matter what happens, whatever theta is, this is still going to be out of the page unless it's negative. And if it's negative, then it's into the page. Okay, so V cross B in a way that it goes into the page would be a voltage, I mean a velocity that points like this direction. Then this is our theta, and V cross B points into the page at that point. Okay, I think that kills it. We've killed it. You have killed magnetism. Okay, now, so what are the units of a B field? B field units. Well, you guys know it's a Tesla. What is a Tesla equal to? 1 Tesla equals 1 Newton per 1 meter per 1 amp. So, but like I said, unit analysis doesn't really help a whole bunch. If you know you've got this equation and you put in all the things that you need, then slap Tesla on the end, okay? And do that, because sometimes I take off points for not having your units. So get your units in there and then box it in. All right? Don't miss out on points just because you're, well, get all the points you can. All right, so we're talking about a B field moving through, a charged particle moving through a B field. I've got something that I want to discuss about this, so I'm gonna do it now. So we've got a charged particle moving through a B field. So let's do what I was going to do in class today, but I'm gonna do it now because I want to talk about what happens and all the forces and all the things that happen. So okay, so let's give ourselves a B field here. This whole region right here is B field, and we're going to set the B field up so that at every point in that region, our B field is pointing into the page, equally into the page, every point, okay? We're going to put, so I'm kind of going back to page 29, okay? We're going to put a charge. We're going to send that charge into this situation. Should we make the charge 1 electron? Okay, let's do 1 electron. It's got a velocity of 1 electron. The velocity is whatever it is, but I'm labeling the velocity with electron on it because it's the electron going in with that velocity. Okay, it's going into the B field. It's going to immediately start to get a force on it as it's going into the E field. So let's look at our charged particle. It just entered It's going in here at this velocity. And what is the force on this guy? All right, so what is the force on it? So first of all, you have to acknowledge that force is equal to QVB. Now the sign of theta doesn't matter because we're doing everything perpendicular to each other, so we don't care about that. It's 1. So QVB, fine. But we do the right-hand rule. So we put our fingers along V. We curl them to B, okay, which is into the page. However, that points our force up, but guess what? Our charge is negative, right? It's an electron. It's a negative charge. So we cannot say that it goes up. It has to go down. Okay? So our force is in this direction. Okay? So we've got our V going there. We've got our charge. That's our charge, and the force is down, which means that this guy will actually start curving, and it'll just keep going in a circle at some point, and that circle will be centered around the middle. And the force that is generated is a centripetal force. So the force QVB ends up equaling force centripetal, and we know what that is. That's MAC, but AC is V squared over R. And there's some radius, R, that this will circle about. So this is really, really, really big stuff. So, fine. Where does that take us? Well, we can do stuff. We can set QVB equal to MV squared over R. Now, everybody knows the mass of an electron. What? You don't know the mass of an electron? What is the mass of an electron? I do know it. It's 0.511 MeV, and that means nothing to you guys. So MeV? GeV? MeV? Anyway, so whatever. The mass of an electron is something we can look up, or it'll be given to you, or whatever. It doesn't matter. The charge of an electron, hopefully you do know the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. Mass of an electron, 9.11. Mass of the electron is 9.11. I'm trying to do this off memory. Times 10 to the minus 27 kilograms. Something like that. It's very small. Okay. So, and then the mass of a proton is roughly 1,800 times the mass of an electron. So, fine. Okay. Boom, 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 boom. So what do? We can take this equation, and depending on what we're given, we can find out all kinds of stuff. One of the things is the ratio of charge to mass. So the charge to mass ratio is something that everybody wants to know. And that ends up being V over RB. So you measure the radius of your curvature. You know the velocity of the thing going in, and you know the B field that it's in. You can get this charge to mass ratio. And this is exactly how I would define a problem if I were going to set up a problem. I know what the charge to mass ratio is, So then I would just make sure that all these things gave me a charge to mass ratio appropriate. Okay, so that's how I would figure out the radius or the B field, or I would say given velocity. This is definitely velocity and not volts. Okay, that's velocity. So, yeah, anyway, you can play around with that yourself and figure out, because we know these things, you can figure out a situation where you know the radius and you know the B field, you figure out the B field, and you can then calculate what the velocity has to be for that situation. Anyway, that's how we learn about subatomic particles. Okay, so I'm going to put this piece of paper back in where it belongs, and I don't know why it's as early in there as it is, but that's how it goes sometimes. So let's get back here. Okay, our Lorentz force law. That's what we just talked about, right? Okay. So that's the Lorentz force law. All right, good old Lorentz. We didn't talk about Lorentz a whole bunch, but he was a guy. He did physics stuff. So let's now get into Ampere's law. And I kind of like my drawings. I did a pretty good job with those. Well, except for the solenoid on the bottom left. That's not looking really great. But Ampere's law. Ampere's law. What is Ampere's law? Okay, it's not one thing. It's a way for us to figure out the B field in many different situations. Okay? Ampere happened to do it for a long straight wire. And Maxwell then turned Ampere's laws into a general situation. But if we have current going along a straight wire, then, and you can think of that current as, so there's two different ways to look at it. We're looking at it perpendicularly right now. We would have, you put your thumb along the current and then your fingers curl in the direction. So here we're going into the page. Over here we would be coming out of the page. And that is the B field. Now, what I've drawn is, so let's go back here, a long straight wire. Okay, that's what our current is. All right. Now, I've drawn another version of it. It looks like a loop, but now we're looking at it from this point of view. So you put your eye over here, and you've got your eyelashes, and you're looking at it with your pupil straight down the barrel of the current. So the current is actually coming straight at you, which means it's coming out of the page. So it's coming out of the page. You put your thumb along that current coming out of the page. So you basically take your thumb and you aim it straight at your face, and your fingers all point in this direction. Every single time, your fingers will point in that direction. Okay, so that's the other picture that I've drawn. This is your B field. The current is coming straight at you, and then it's all the same R away from that current. Okay, it doesn't look like it's the same R, but it is. That's the same R all the way around. Okay, the wire that is aimed straight at your eyeball. Okay, so two ways of looking at it, and they're definitely drawn there for you. I just didn't do a good job of describing what those pictures were. So this is us looking at it straight down the wire. And then the other picture is us looking at it from, here's our eye, here's our eyelashes, and there's our pupil, and we're looking at it like this. So in one picture, this picture is this, and this picture is this. I think you guys get it. I hope. It's hard to do. You got to give me some credit for this. I did pretty well, I think. I'm going to call it a win. I'm walking out with a win on this one. A loop of wire is a similar situation. However, the loop of wire is one loop. So we've got our loop. So we've got current coming in, current going out, and it's a loop. So you put your thumb along the current, and you curl your fingers. So on the outside, it's going to curl in. On the inside, it's going to curl toward your face. So the B field on the inside looks like this, and the B field on the outside looks like this. Cool. If we were to look at it from a different angle, so we've got our in current and our out current, then we'll go in here, out there, and we put our thumb along that, and we would have on the inside our B field going up on the inside, and then it would be going like this and down on the outside. Just like I showed over here, but hopefully in a more three-dimensional way. Okay, so good on us. Now, as the Aussies would say, what does Ampere have to say about all this? Well, Ampere says that our B is equal to mu naught I over 2 pi r for the long straight wire. Here's our radius r. We know what mu naught is. Mu naught is a constant. 4 pi times 10 to the minus 7. Is that right? I think so. Okay, so we've got mu naught. We've got our current I that are both given. And we've got some radius r away. This is the radius r away from that guy. For a loop of wire, our B is equal to mu naught I, where the loop radius is r, and we're going to divide by 2r. So there's two different ways of doing it, and I think now is a good time to stop, and we'll come back and finish a little bit with the solenoid, talking about how we produce a uniform B field down the middle of a solenoid.